हेलो स्टूडेंट, मैं हूँ अनीशा एंड मैं आज आ गई हूँ एक नया लेक्चर लेके एंड आप सब लोगों का मेरे चैनल पे स्वागत है। तो आज की जो वीडियो है वो रोटेशनल स्पेक्ट्रोस्कोपी का सेकेंड क्लास है एंड इट इज़ वेरी इंपॉर्टेंट टू नोट कि ये वीडियो बहुत ही बेनिफिशियल होने वाला है for both the graduate student and the student who are preparing for the competitive examination like NET, GATE or SET and all. So actually in the previous class we have learned how to derive the energy level expression for the rotational level, and in today's class we will focus on the what is the practical use of that energy expression कि हमको वो एनर्जी एक्सप्रेशन जान के क्या होगा। हमने तो डिराइव कर लिया, तो क्या होगा वो एक्सप्रेशन जान के, उसी सब भी मैं आज बताने वाली हूँ आपको। तो सो एट फर्स्ट आई विल लाइक टू टेल यू कि इन द लास्ट क्लास वी हैव डिराइव्ड द एनर्जी लेवल एक्सप्रेशन विच इज द रोटेशनल एनर्जी लेवल एक्सप्रेशन, दैट इज ई जे इज इक्वल टू 8 स्क्वायर बाय 8 पाई स्क्वायर आई j into j plus 1, where here h is the Planck constant, I is the moment of inertia and j is the rotational quantum number. So this is the expression for the energy expression for the rotational level. So in the previous class I explained in detail the derivation of this equation. If you did not see that video, please check it out. Now this expression is in terms of the joule. So if we want to convert it in centimeter inverse, then the conversion rule also I have explained. So for if we convert it in the centimeter inverse, then it will expressed as small ej, which is equal to h by 8 pi square I c j into j plus 1. Now this part is constant for a particular system. I is moment of inertia, c is the speed of light. So this part is constant for a particular system. So in simple form I can write Ej is equal to B into J plus 1, which is in the centimeter inverse. So this is the energy expression for the rotational level. So where J is equal to 0, 1, 2, 3 and all. Now when J is equal to 0, then the energy E0 will be B into 0 into 0 plus 1, that means 0. So the first rotational level, that is when J is equal to 0, the energy value is also 0. Okay. Now consider when J is equal to 1. When J is equal to 1, then E1 is equal to B into 1 plus 1, that is equal to 2B. Now the first excited state is the 2B. Here J is equal to 0, here J is equal to 1. Now when J is equal to 2, then what is the energy? That is E2 is equal to B into 2 plus 1, that is equal to 6B. So then that is J is equal to 2 is equal to 6B. Now when J is equal to 3, then E3 is equal to B into 3 plus 1, that is equal to 12B. So it is somewhat here, that is equal to J is equal to 3, that is equal to 12B. Okay. Now another level, when J is equal to 4, then E4 is equal to B into 4 plus 1, that is equal to 20B. So this will be 20B for J is equal to 4. So these are the rotational energy level. And what is the energy of the particular rotational for the particular rotational quantum number we get from this energy level expression. For 0 that is 0, for 1 that is 2b, for 2 that is 6b, for 3 that is 12b, and for 4 that is 20b. Now interestingly, in spectroscopy, whatever I have told you, that is spectroscopy is the interaction of light with matter. So in case of the rotational spectroscopy, when we give some microwave energy to the system, so it will absorb that microwave energy and it will excite it to an higher energy state. Now very interestingly, in case of the spectroscopy, there is some selection rule, that is after absorption of that particular amount of energy, the system will go higher. Okay, so there is some selection rule. So if I provide some amount of energy, then मान लो कि मैंने कुछ माइक्रोवेव एनर्जी प्रोवाइड किया, सो पहले सिस्टम जीरो एनर्जी स्टेट में था, स्टेबल था. नाउ वो एनर्जी लेके वो इधर भी जा सकता है, इधर भी जा सकता है, इधर भी जा सकता है, इफ देयर इज नो सिलेक्शन रूल. देन if there is no selection rule, then situation will be very much complicated. So we cannot tell that is from where to where the transition takes place. That's why very interestingly, and we are very lucky as a chemist कि स्पेक्ट्रोस्कोपी में कुछ सिलेक्शन रूल होता है एंड मॉलिक्यूल वो सिलेक्शन रूल वाइज एनर्जी को एब्जॉर्ब करते हैं और एनर्जी को एमिट करते हैं. सो बट इसका मतलब ये नहीं है कि इट इज़ एन हार्ड एंड फास्ट रूल, दैट इज हमेशा ये सिलेक्शन रूल मॉलिक्यूल मान के चलता है. देयर आर सम फॉरबिडन ट्रांजिशंस ऑल्सो, बट इन केस ऑफ allowed transition, when they are following the selection rule, then the intensity of that particular band will be very much intense. But when there is forbidden transition, the intensity of that particular band will be very much weak. Now in case of the rotational spectroscopy, the selection rule is कि now del J, that is the change in the rotational quantum number, the del J will be plus minus 1. Selection rule very important. Please note it down. The selection rule for the rotational for the rotational transition is del J is equal to plus minus 1. And another important thing is that this is true for the rigid rotor. Now what is the rigid rotor? I will tell you later. So for the rigid rotor, the selection rule of the transition between two energy level is del J is equal to plus minus 1. So if we provide some amount of the microwave energy, then the transition from this place to this place will take place. But this transition is the forbidden transition. But this transition is forbidden. But the transition from here to here can take place, because for this transition del J is equal to 1, for this transition J is equal to 1 to 2, then also del J is equal to 1. That del J means the change in the quantum number, because J is equal to 1 to 2 means the del J is equal to 1, 2 minus 1. And this transition is also allowed, that is del J is equal to here also 1, 2 to 3, and this transition is also allowed 3 to 4. So this type of transition is allowed for the rigid rotor according to the selection rule. So here we have seen that J is equal to 0 to 1, J is equal to 1 to 2, J is equal to 2 to 3, and J is equal to 3 to 4 is allowed. Now from the energy expression we can calculate what is this amount of energy. That is, if a molecule is from ground state, it will go to the first excited rotational energy state. Then for that, what amount of energy it will absorb, it can be it can be calculated using this formula. So now I will show you how to calculate this. Okay. So the selection rule is del J is equal to plus minus 1. Please remember it. Now the rotational energy expression, again I will write the same thing, B into J plus 1. So the allowed transition is J to J plus 1. This is the allowed transition because here del J is equal to 1. J to J plus 1 is allowed, or reverse is also allowed, that is J plus 1 to J is also allowed. Okay. So these are the allowed transition where del J is equal to plus minus 1. If we consider the transition from J to J plus 1, so for the J level, this expression will be Ej is equal to B into J plus 1. Now J plus 1, this expression will be B into J plus 1. Now J is equal to J plus 1. J plus 1 plus 1, that is B into J plus 1 into J plus 2. The rotational quantum number is J. That's why I put it J into J plus 1. But here the rotational quantum number is J plus 1. That means I have to put in place of J, that is J plus 1 plus 1. Now what is the energy gap? That is del E. Del E is equal to E J plus 1 minus E J. So that is B J plus 1 J plus 2 minus B J into J plus 1. So the common factor is B J plus 1, then J plus 2 minus J. So this is 2B J plus 1. So del E is equal to 2B J plus 1. Okay, understand? If the transition is from J to J plus 1, now the del E is the 2B J plus 1. This is very important. In NET, GATE or any competitive examination, numerical comes from this part. That is, you have to remember that equation, that is del E is equal to 2B into J plus 1. Okay. Now consider this transition, that is J is equal to 0 level to J is equal to 1. So now J is equal to 0, put as J is equal to 0 from this equation. So for this transition E 0 to 1, for this transition if I put J is equal to 0, then del E is equal to 2B. Del E is equal to 2B. Now consider this transition J is equal to 1 to J is equal to 2. That means the J value is 1 here. So then del E 1 to 2 is equal to 2B 1 plus 1, that is equal to 4B. That is equal to 4B. Now consider this transition, that is J is equal to 2 to J is equal to 3. Put J value as 2. Then del E 2 to 3 is equal to 2B. 2 plus 1 is equal to 6B. So the transition is, so the difference is 2B, 4B, 6B. And here also 3 to 4, then it will be del E 3 to 4 is equal to 2B 3 plus 1 is equal to 8B. So here I am putting J, the lowest J value. This is J. Actually, in case of the derivation of this equation, we have considered J to J plus 1. So here J is the lowest value. This is J and this is J plus 1. From the rotational spectra, we'll get some line. So in the rotational spectra, we'll get some line for these transitions, that is from J is equal to 0 to 1, 1 to 2, 2 to 3, 3 to 4, and this line will be situated in this manner. For this is the, in case of the 2B, if this is the 0, So this will be 2b. Now next line, this is for 0 to 1 transition. Next line will be in 4b because the total is 4b. Total is 4b. This is for 1 to 2. Then another line we will get for 6b. The total is 6b. That is the j is equal to 2 to 3. Another line we will get for 8b. The total is 8b. And this is will be for 3 to 4 for this, and so on and so forth. So for these transitions from j is equal to 0 to 1, 1 to 2, 2 to 3, we'll get some line which are situated in this manner. Okay, and interestingly here all line, the gap between all line is 2b. The gap between all line is 2b. Okay. If we consider from j is equal to 0 to 1 transition, the gap is 2b, now it is 4b. So 4b minus 2b is equal to 2b. 6b minus 4b is equal to 2b. 8b minus 6b is equal to 2b. So the gap between rotational energy line, whatever we will get in the rotational spectra, the line are equally spaced line. The gap is the 2 into b, 2 into b, 2 into b, and 2 into b, and so on and so forth in case of the rigid rotor. So now from the spectrum we will get this gap, that is the gap between two lines. So from the gap between, if we get the gap between two lines from the spectra, we know from this all calculations this gap is equal to 2b. So suppose this is equal to x. So we know 2b is equal to x. If we know the gap between, we will get the gap between two lines from the rotational spectra, and this is, suppose this is x. Now consider the formula for b. B is equal to h by 8 pi square I into c. Now here h is constant, c is constant, 8 pi square is also constant. Now I is equal to mu into r square, and mu is the reduced mass, r is the bond distance of that particular molecule if we are considering the diatomic molecule. Okay. So in case of the diatomic molecule, the I is equal to mu into r square. Now for a diatomic molecule, you are using a molecule, suppose you are using the carbon monoxide. So for the carbon monoxide, you know the atomic mass of the carbon, you know the atomic mass of the oxygen. So from that atomic mass you can calculate the reduced mass of that system, but the bond length is unknown. Okay. So from the energy gap between two rotational lines, you can, here the only unknown factor is the r, that is the bond length. So from the energy gap between two rotational lines, you can calculate the bond length of that molecule. Okay, समझ में आया क्या? Just put the what is the b, that is h by 8 pi square I into c, which is equal to x, and x you will get from the rotational spectrum, that is what is the gap between two lines. Then here in this equation, that is h by 4 pi square mu r square into c is equal to x. Here only unknown factor is r. So from that equation you can calculate what is the bond length of that system, what is the bond length of that molecule, whichever you are investigating. So this is one aspect for the rotational spectroscopy. So in the next video I will solve some numerical by using these concepts. Okay. So that's all for today, students. Hope you enjoy this class, and thank you for watching. If you like my videos, please do subscribe my channel, and that's all for today. Namaste, Jai Hind.